Do you want me to wait a bit for people coming?
No, I think you can start. I'll
Okay.
I'll get him.
Okay.
You please start, yeah.
Okay. Thank you, everyone.
Yeah, the talk has started. Please come. Yeah, please. Please
The talk has started. So yes, hi everyone once again. So I'm going to give you a kind of an overview of what we're at the moment doing in the LSST desk time domain analysis, how the pipeline is working, and what's the strategy for supernova cosmology and what we foresee, and et cetera, et cetera. This, as the title over here says, it's a fully photometric approach because LSST will be heavily invested in photometric supernova cosmology analysis. And so I come from University of Illinois, NCSA. I'm a pipeline scientist in LSST desk. This work that I'm going to talk is an ongoing process analysis with me, my principal collaborator, Richard Kessler from U Chicago, and the wider LSST desk time domain people. Before I go into supernova cosmology itself, I would like to run through a very quick recap of what LSST is for those of you who might not be familiar with it. So LSST is, like the map shows over here, so it's an observatory which is being constructed, and it's currently already in the operational phase in the Atacama deserts of Chile. It's housing a 8.4 meter class state-of-the-art telescope with arguably the world's strongest camera on board, which is 3.2 gigapixel. Has a huge structure, 35 tons of size of telescope dome. Apart from the optics and the astronomical part, the computational aspect of LSST itself is also state-of-the-art, cutting edge. It will observe terabytes of data every night, and the computational facility itself also is a huge boost to the community, that the research on that aspect. And also it has a substantial global footprint, and it's an ever-growing family. Like it's already 3K plus. I might be wrong, maybe a few more Ks are there. Anyway, this is how the cross-section of the LSST observatory looks like. Some of you might be already probably have seen more real photos. It's a huge structure, 36 ton. Moving it is really a challenge. I was told that the main, this dome, when the camera, when it was moved from SLAC in California, Stanford, all the way to the site in Chile, a full Boeing 747 was rented to just take that thing all the way there. And there was a makeshift landing strip made in the deserts over there. However, in spite of its huge size, it is quite swift in its operations. For example, like it says, it can scan through the sky in few seconds. And then basically it will go and do this thousands of times every night, multiplied by over its period of runtime, which is 10 years of lifetime. The LSST network is like this. Of course, Chile housing it has one of the principal partners to it, but the head office is in the west coast of US in California. I think this map is, this plot is a bit backdated, but that's the best I got at the moment. So the data facility over here shows it's NCSA, where I come from, but it's not. It has changed since then. I think it's with Noir Lab or somewhere else. The French also has active participation to it. And one interesting fact I heard, I don't know how much truth is to it, is that there's actually optical fiber cables running all the way under the ocean, all the way to Europe. So it's huge, in short. The LSST, I often bring this analogy. It's like a conglomerate under which there's individual science-focused groups working, as you can see by the names, which are kind of self-explanatory. It is similar in analogy, like if you can think of Alphabet, and under which there's like Google and every other independently working with their own goals. So there's, for example, AGN, Solar System, etc. And then there's DESC, which stands for Dark Energy Science Collaboration. As the name says, it's self-explanatory. It is in DESC that I work. So the LSST is a broad mission, like I've been mentioning. So it will scan the southern sky over its period of 10 years of lifetime, 18,000 square degrees of the sky. But apart from that, it also has some additional pencil beam-like surveys, 5 patches in the sky, where it will zoom in and it's like 10 square degrees and have additional science goals over there. First slide, many of you are aware that June this year there was this the watch party for the LSST because of the first slide that happened. And the 1-year data release we're expecting somewhere about a year from now, or in 2027, early 2027. So the current status at the moment is, like I mentioned over here, that we saw the system first slide somewhere in June, July this year. And it's already in the operational phase. 1st of November, the early operations have started. So next year, summer, we can expect what we call as the DP2, which is the data preview from the early commissioning stages, and then the actual data release, like I mentioned in the previous slide, somewhere end of next year. That's why we finished with a brief recap of LSST. Now I come to supernova cosmology with respect to LSST. So when we talk about SN cosmology in modern era, meaning in, let's say, last 3 decades or so, broadly, for the best part of the last 2 decades, when someone is talking about SN cosmology, we're talking about using spectroscopic data, often being called as the gold sample of the data. So all these seminal papers that you see on the right, including the Nobel Prize, and you name it, JLA, Pantheon, PanSTARRS, Dark Energy Science, 3 years data, they all fall in this category of having a spectroscopically identified sample with spectroscopic redshift, very pristine quality data. But as our telescopes got bigger and our chips are getting stronger, the CCDs, the data gathering capacity, everything is getting more stronger, we were now detecting much more objects than were in those days. And so what that means is that now we have further bigger samples where spectroscopic follow-up of all of them is not practically feasible. So we will have a lot of what we call as photometric events. And so the community started exploring, can we also use those photometric events usefully in our cosmological analysis? Because as obvious, the photometrics comes with its own challenges of errors and systematics, etc. So different combinations people have been exploring. For example, can we use photometrically classified supernova but still having spectroscopic redshift? PanSTARRS 1 by David Jones in 2018 showed some early explorations of that. And the most recent one is the Dark Energy Science 5 years data release last year by Maria Vincenzi et al., where they successfully showed that you can actually use photometrically classified supernova but still having spectroscopic redshift to do feasible cosmology and dark energy analysis. The alternate combination you could also ask, can we use photometric redshifts and do good enough cosmology with it? Not much analysis has been done until like we did this again in 23, but using LSST DESI simulated data like end-to-end comprehensive analysis, where I showed that yes, using photometric redshift, we can actually do feasible cosmology with supernova data. Now, all this is, as you can see, evidently is culminating to the final step. It's like, can you do a fully photometric analysis? Meaning, can you do photometrically classified photometric redshift? And if you do that, that's like the final nail in your coffin. It's like all this last 2-3 decades of survey and effort is the pinnacle to it. So this is what we have been doing, and this is what the topic of today's talk will.
What about Zwicky?
Yeah, I mean, Zwicky features, well, let's say we can put it.
They're talking about tens of thousands of supernovas.
We have some tensions with Zwicky, so.
I know.
Yeah,
We're working
yeah.
on the second data release, which
Yeah.
they say will fix the photometric.
Yeah, so from our point of view, I think there's a lot of inconsistencies. So I'm aware what they're doing, but we can talk about it also. Yeah. And so, as far as I know, so this analysis that we're going to show now, apart from, and then there's a recent another paper by Richard Kessler, my collaborator, using Raman similar data. I think this is the only two state-of-the-art fully photometric supernova cosmology analysis that has been happened till now. As I'm saying, as luck would have it, it's only today morning, an hour back, this paper now appeared in archive, so I think good timing, so advertising. So before I go into this, I would like to just remind you a couple of jargons that will continuously keep, yes?
Even when you say fully photometric, it says spec or photo.
Right.
So you are hoping that somebody will point a spectrograph at it and result to some
No, it's
alert you send out and give you spectrometric.
it's more it's okay. It's simpler. It's you will have your resources to have some spectroscopy. Those that you cannot will be photometric. So when I'm saying spec or photo, meaning that in spite of taking, I'll still have my best gold standard data, but the additional I'll also use them. I'm not just saying only photo.
What fraction is still spec?
So the rough forecast at the moment is with DDF, you can probably have 10% of spectroscopy. Yes. So we'll have plastic, elastic, all these terms going frequently. This is very LSST specific term. So plastic as is an acronym standing for Photometric LSST Astronomical Time Series Classification Challenge. So it was given as a global data challenge in Kaggle, basically for classification of transients. We used that in our previous paper for having the data of light curves, etc., from generating from those. And then elastic, in a way, you can think of as a version 2 of plastic, which basically, like the name suggests, is an extended plastic. So hence more realism is added into it. The LSST has done it over the last 5-10 years. So it's like it has iteratively produced simulated data with more complexity and realism added to mimic close enough what would be when it goes live. So, so we have used those data, those for our data sets in the analysis. So also, again, going before into this fully photometric analysis, I'll lead you from the previous analysis, M23, as it sets the platform. So I'll also again give a brief recap of what we did over there. So in M23, we use the DDF. The DDF stands for the deep drilling field, like I mentioned in the first slide, like this pencil beam surveys. We use the DDF seams and we use photometric redshifts. But we use supernova 1A only in that, meaning there is no contamination in your source. So there's only type 1A, so spectroscopically classified samples. And we use spectroscopic redshift using foremost forecast, and when not available, photometric redshift was based on Melissa Graham's analysis and paper from 2018. All of this is then being tied into the time domain pipeline of LSST, which under the hood is using SNe Ia to do the analysis. This is what a modern day supernova cosmology analysis pipeline looks like broadly, like anywhere. They might have some deviations, but this is what the general steps are. So you'd have a simulation. So we like I mentioned, plastic, we do a plastic supernova 1A simulation, then we do an additional supplementary low redshift spectroscopic simulation. There's something called the bias correction, very specific to supernova 1A. So for that, we need to generate a high-stat sample. And then you come to the light curve fitting stage. The standard rule of run-of-the-mill light curve fitting at the moment in supernova cosmology is using a solve to fit and then do a chi-square and then get the light curve fitting. It uses 4 parameters, like the standard 4 parameters of the supernova fit. In our case, we used a 5-parameter fit, and the 5th parameter was the novelty of that work, which is the photo Z. This is why your photometric redshift information comes into your light curve fit. Photo Z of the host galaxy redshift. Then once you do the light curve fitting, you get the trip equation, distance, etc. Then you correct for your selection effects, etc., etc., and then you get a Hubble diagram, which is the basic standard primary objective of doing a supernova cosmology, your distance estimation. So you get the Hubble diagram, you treat it, and you correct for the selection bias contamination, if there is, which was not there because it was type 1A. So you do those. Then you come to the next step, which is doing a covariance matrix, take into account all these systematics and statisticals, etc., and then a standard cosmology fit with CMB prior or CMB, etc., and you get a dark energy estimation. That is broadly what a supernova pipeline looks like.
What about this claim that there is a correlation of the absolute magnitude and the progenitor age, that the Korean group has been, in principle, you could incorporate it at this level if you wanted?
You could. So we did mention in our paper that there's a lot of, one side is there's a lot of systematics we did not consider because we are setting the baseline at the moment. And one of those is that, and it's a study for another case, people can do that. We haven't explored because we're just setting the road, so yeah. So using that in the previous analysis, this is what the Hubble diagram looked like. So for example, on the left, what you see in red is the spectroscopic, like it's mentioned, Z spec. On the right is a Z photo, meaning it has all of this plus additional photometric samples were there. The bottom panel shows the Hubble residual, which is basically mu minus mu true. So what the two main things that you take away from this, is that when you do a photometric Hubble diagram, you see your Hubble diagram extends further beyond on your redshift axis compared to your spec-only analysis. And basically, there's no obvious systematic trends over there, which is quite assuring as that if you do a photometric analysis, there's no road mines. Simulated. This is all simulated, LSST simulated, yes. We generate this spectra. We generate everything in the LSST time domain pipeline based on survey conditions and systematics considered, et cetera, et cetera. This all sim.
Yeah, I'm just trying to understand that. So the basis of the simulation is that that have already been observed.
Sorry?
The basis of the simulation are the supernova that have been observed by previous surveys, or it is something else.
So there's no one answer to this. So for example, in the simulation, you have multiple consideration and assumptions. For example, you assume a rate of supernova, volumetric rate, etc. You assume your different kind of, let's say, systematics, which has information that it inherits from previous surveys, let's say from Pantheon and DS. A lot of those mix and match. And then also survey design influences a lot of those. So all of those combined, you come to a point. It's not a single one-point answer that it's based on previous thing. It's a mix of both.
So does NANA just spit out the light curves in different bands, or does it actually generate photons according to some granular spectrum that is then binned into?
No, it generates the light curve. Yes.
So one of the things I've heard supernova cosmologists say is that the spec Z has high uncertainty while the explosion is happening because there is, I mean, you can't narrow down on lines in the period immediately after the explosion. Are the physical reasons for such things modeled in SNeIa correctly? If it is
Yes, again, you can. SNeIa has those options. We purposefully don't add those complexities at the moment, but you can, actually. Yeah, there's a lot of things, yeah. Shall I move forward?
Clarification question.
Yeah, I mean, yeah, that's fine. So all that leads to dark energy estimation. So what the main takeaway from that previous analysis was that, so what you see over here is on the dark energy W0, WA plane, the estimations of, so there's a pair each in red and blue for solid and dashed ellipses. So what the red is corresponding to the spectroscopic, like as the previous Hubble diagram was, and the blue is in for the photometric sample. And then the dashed is stat plus systematic covariance. Sorry, the solid and the dashed is stat only. What it shows over here is like we show the figure of merit, which is computed using this dark energy task force equation expression, and basically says that the blue has always better figure of merit corresponding to its red counterpart, meaning that if you do a photometric analysis, you can have better dark energy estimations. So higher the FOM, the better it is compared to a spec-only analysis. So much so that we show that you could have an improved figure of merit of almost 40% if you do a full photometric photo Z analysis with spectral supernova. main conclusion over there was that adding SN plus host photos significantly improves average distance measurements for Z of greater than 0.6. Your figure of merit in the dark energy is improved by substantially, 50%, and your Hubble diagram now extends like quite further in the redshift axis. All this now leads us to the current analysis, which is a fully photometric. So for example, over here, we only had a photometric redshift, but type 1 is only. So now the additional layer of complexity that's being thrown on top of that in the pipeline is, so we include photometric contamination, meaning you can have non-1s like core collapses, peculiar supernovae, etc. in the data set. Host galaxy misassociations, etc., etc. Of course, because we're using from plastic to elastic, our photosy modeling has improved. So again, another slide dedicated to this was the main improvements. So do I have like 10 minutes, 15 minutes?
Yeah.
Okay, fine. So the main improvements, like I mentioned, so you have the contaminations, you have now more realistic cadences. There's something about the Hubble diagram. Classically, the Hubble diagram has been constructed doing is beamed analysis. Like on the redshift space, it's beamed, and you give a beam distance estimates. But there's a famous paper by called Binning is Sinning, where they showed that if you do unbinned analysis, you get better figure of merit. You have less washout of your data information. And so we also provide an unbinned Hubble diagram analysis. There's also some concept called the rebinning, which also has its roots from another paper, which is called Binning is Sinning to Redemption. And so the redemption is the rebinning. So we also do that. So taking all these complexities now into account, in addition to having contamination in your analysis now, meaning it's a fully photometric regime for SNe cosmology, our pipeline now, if we revisit the pipeline's flowchart, it's still the same pipeline, but now there are additional layers of complexity. For example, your simulation now has 1s, non-1s. You have this additional stage in between where you have a photometric classifier. The classifier caters to identifying a given object as 1A or non-1A. We use the software we use is called SCONE, but it could be any classifier if it satisfies. And then you have the BBC and the Hubble diagram, where the BBC now has to cater for the contamination and correct for those before your distance estimation in the Hubble diagram goes into cosmology fitting. Just a slide on the photometric classifiers motivation. So large number of supernovae is more relevant in the LSST era, as will not be possible to be spectroscopically followed up. So it's if you were to take leverage of your photometric sample, you have to use a photometric classifier. And additionally to that, recent advancements in your neural networks and the photometric classifiers based ML-based techniques, etc., have showed that the contamination or the effect of uncertainty from a photosy classifier is not the principal culprit in your systematic budget. There's a very nice paper from Anne Smola where she showed that if they were to use a photometric classifier, they could use additional 700 supernova in the DS 5-year analysis on top of what the DES paper showed in the cosmology results. So leading to that, so now this is how our photosy classifier performs. So we used 50,000 type 1s, 50,000 non-type 1s to train our classifier. And we achieved about 98% accuracy on both training and validation. And so there's no hiccups over there. So basically what SCONE does is, SCONE is the name of the classifier that we use from someone else who has developed it. It's basically given an event, it provides whether it's the probability of it being a 1A or non-1A, like you see over here. True 1A is on this right edge and non-1 is on the left edge. Once you get all those probabilities out from a classifier, you have to tie all those information to something called as beams to be able to use them or transfer it to your distance modulus estimates. So what you do basically over here, like you said, so you get the photosy samples, you do a classification, then you determine the supernova types, meaning you get those probability values, and then you use what is called beams. So beams is people generated like Martin Kunz, René Lozic, etc. They generated for a broader suite of things, but we adapted it for supernova cosmology beams with bias correction, typically called BBC, where those information of the probabilities are being fed in like this. So these P's come from SCONE, and then you get a P of beams, which is a single point. Thank you. And then everything together, you can have something where you can add a correction to your distance estimates based on, yes, please.
Have you got any trade-off to have a lower recall but no false positive?
Lower what?
I mean, basically having less number of cases that you can classify, but basically eliminating any false positive.
Yeah, you can always do that.
Less part one, but making sure that there is no contamination.
I'll come to that later. Yeah. So once you get that, so BBC then uses the scone predicted probabilities to determine the beam's probability and produce a bias corrected distance estimate. So what you see over here is like this is your redshift axis, and this is a sigma of mu. So sigma of mu is basically the uncertainty on your distance estimation, right? And what's noticeable or you'd like to see is that as you go in towards the higher redshift, where it's more populated by photometric candidates, your sigma of mu is well behaved, which is basically the goal we're trying to achieve. And on the top panel, we show the statistics of in each of those redshift beams. Coming to Arman's point, if we were to, let's say, overplot on this, just as, let's say, a spectroscopic sample, then you'll see your sigma of mu is very good at the low redshift because you will have, or maybe, okay, I'll come back to that with a separate plot. I'll just not sway at the moment. So your final sample contains a mix of spectroscopic candidates at low redshift, like you see in the blue, and then you have more photometric candidates populating your higher redshift as you go towards the right edge of your z-axis. So for the covariance matrix, the systematics that's been considered broadly can be the calibration systematics, redshift systematics, etc. We combine all of those, and then we do move towards a Hubble diagram. And this is how the fully photometric approaches Hubble diagram looks like at the moment. So for example, you have your blue points, which is your typical 1As, but then you also see you have those bunch of red points, which corresponds to, like the color bar shows over here, it's a 1, P of system is probability of being a core collapse is 1. So those are the contaminations in your Hubble diagram. So about 11% of non-1 we found over there. And this is a residual. The residual, we did fit a linear slope just to see how the trend looks like. Is it like completely systematic free? We do find a small bias over there. We're working on this, but yeah, it is what it is. The binning method, like I mentioned, I'll just run a bit fast now. So we mentioned that there's a binned and unbinned and ribboned analysis that's been done. The ribboned analysis basically is on the unbinned on top of you put additional, you do another binning on basically in the stretch and color space. So it gives you a middle ground between binned or unbinned. So you have more computational time or lesser overhead charge, but you also get better constraint than a binned Hubble diagram. So this is how a fully photometric analysis dark energy estimation looks like at the moment. So what you want to see over here is on the left is a stat-only covariance considered. It's a stat plus syst. But as you move from left to right, so in the insets you have these crosses, which corresponds to like the biases for average 25 of data sets, meaning that we had run individually 25 parallel runs, statistically independent, and then we took the mean of those to compute the mean WAs. And for each of those three cases, binned, unbinned, ribboned. So main takeaway over there is like if you move from binned to unbinned, you get like a 30% improvement in your figure of merit. The conclusion at the moment is so basically like using photometrically classified supernova 1A and having photometric redshift in the LSST era is very much a feasible option for doing cosmology. Photometric supernova 1A data set with photometric redshift can give better dark energy figure of merit, like you saw. Your ribboned Hubble diagram analysis has been established, showing that it can replace it. Why I'm saying it can replace, because if you have an unbinned analysis of, let's say, 6,000 supernova, your covariance matrix is 6K times 6K. The inverting it and etc. is a huge computational challenge, but the ribboned analysis gives you the space for that. I would like to give a big fat warning that while this all looks fine, but this also needs to take into account that this is a simulation. And so the challenges of real data analysis is still looming large. So we're working on it, but hopefully this will stand out when in a year's time where we see the real data. Before I conclude, I would just recommend give a couple of slides. So what to expect in future? Oh, that's fine. What to expect in future? So for example, this is a plot that we're also working on the paper. So So this is my colleague, Lyman. We combined in the next generations, for example, supernova with LSST, next generation of CMB from stage 4 like SPT or SO, and then we also combined with BAO from the DESI DR3. And you want to see in the green one, it looks very exciting. Also, there's this question ever since the DS plus DESI results of BAO came, and then we have seen our previous speakers as well about deviation from ΛCDM. I cannot comment on that because we're using a similar data sets, but what we can do is like we swapped the DS 5-year with the LSST sim that we've been using in this paper. And what we find over here, keeping everything else same, we find that we can have in the LSST area probably about 1.5 to 2 times the improvement in the figure of merit on dark energy estimation than what the current shows. Again, I'm not going to comment about deviation from ΛCDM because we're not there yet. So what the future looks like if we were to get data next year, then we comparing with our previous peers like SDS, SDES, we think will take 5 years. So about 2030, we're looking at a timeline when we can have some first results of LSST supernova cosmology analysis. And before I finish, like what are the other desk efforts that we are working on and very much invested in at the moment? Previous speakers spoke about SBI, etc. So we are very heavily invested on that. So using SBI for addressing supernova selection effects, replacing bias correction techniques, etc., likelihood-free approaches. We're also very much invested in using foundational and explainable AI to explore nature of dark energy, which is without human priors imposed on that. And before I finish, I don't know if I have time, by the time we anticipate the LSST results come out in 2030, it will be about 100 years when Edwin Hubble produces first Hubble diagram in 1929. And so this became quite a hit. So we compiled a set of Hubble diagrams over the years. And I'd just like to leave it over there for you to see what can be expected as evolution of Hubble diagram in the last 100 years. So this is a Nobel Prize from Perlmutter. We have the celebrated JLA, which I think Subhi showed in the first presentation. We moved to Pantheon, Pantheon Plus, DES, and then we're holding our breath for the LSST in 4 or 5 years' time from there. And thank you.
Question? Okay, let me start with someone who is not asked. Yes.
So the photometric efficiency you showed, like the improvement of figure of merit, was it true for the DDF or for the wide field deep?
So it is true for DDF about the wide fuzz deep. We have wide fuzz deep considered only for the low redshifts at the moment. And part of the reason of this is, of course, you can say you can use it for the full redshift spectrum of wide fuzz deep. We don't anticipate that the first cosmology result will be using that. We think it will be a DDF-heavy data set with some low redshift WFD. So what we show is what will be maybe in the later future WFD full sample analysis, which you hear from people a lot, like there will be millions of supernova, but we don't think we'll be using those number of supernova for the first year's cosmology results. So what you show here is a DDF and some low redshift WFD efficiency.
But it can be used for WFD as well, right?
It can, it definitely can, but we're not considering at the moment for the cosmology analysis results for the first year at least, yeah.
Ramesh?
So in one of your plots, the redshift was labeled ZHD, and in another one it was labeled photo Z. And I'm aware of the evolution of the redshifts used in JLA with ZCMB, and since we work on peculiar velocities and its impact on the Hubble diagram, we have some, difference of opinion with the supernova community on how the redshifts are to be corrected, which actually go back to the fitting problem in cosmology by George Ellis. Could you comment on how you're simulating peculiar velocities? Is there a coherent component? Is the coherent component which Rick Watkins spoke about, which exists at more than 4 sigma in the local universe, now something you intend to take into account? Because that's now an aspect. If it crosses phi sigma, then you have to accept it as an aspect of reality that is actually there, and then you have to kind of simulate the local universe in a manner of speaking, at least for the low redshift supernovae. So,
Yeah, so...
So just a short answer. I mean, this question will probably needs a lot of discussion.
Yeah.
Then further, you can just short answer to that.
So also before I start, I want to mention that there's a giant in LSST desk called Alex Kim, who is working full-time on exactly on this. So if someone wants to reach out to Alex, he can give you, like, he's fully devoted on doing this. Peculiar velocities and Z and the corrections in the low redshift era in the LSSTs. And there's a separate group on that. Yeah, I kind of forgot what you asked.
I asked, what are you putting? I'm assuming ZHD in the simulation is just what you're getting from your FLRW
Right.
that you're putting. And so it is in the cosmic rest frame.
Yes.
Yeah, but
Yes.
there's no cosmic rest frame in reality. So.
He's asking because he showed earlier
I know.
what Kessler had done was not right for JLA.
I know where he's coming from.
We have learned the lesson.
Yeah,
No,
yeah.
I don't think so. I think this is a lesson that is going to be quite painful
The
to
only
learn.
way you can do that is to get into the collaboration and work with.
I think you're already part of
Yes.
the
Yeah, technically, but
Yeah.
And you are more than welcome to come and join us. Like,
Sure.
yes, yes, yeah.
Don't snipe from the
Yeah, yeah. So, Nyash, is your question answered, in which you had asked earlier? Yeah, okay.
So I think my worry with the photos is that it's based on some spectrum. That, I mean, the idea is that you think you know the spectra of the objects you're looking at, in this case supernova. So if you observe the colors, that's enough for you to...
The photo Z is from the host galaxies, mostly. And the host galaxies there's catalogs called the elastic, like I mentioned. So they're based on Pan-Star Swan analysis people, where they used to have some 16,000 or 20,000 host galaxies, from which there's a dedicated group called RAIL in LSST Photo Z, where they extract the Photo Z information from there. So to come back, sorry to cut you, but I think it's mostly host galaxies. So I think
So you wait for the supernova to kind of die down and then look at the galaxy and then infer the photo Z?
Yes and no. I mean, if you get a supernova host photo Z itself, it's good. But mostly, we used, like, I think the main even the headline is like host galaxy photo. We just focused on the host galaxies to get the photo Z on that prior on the redshift.
Right. Okay. So, but I guess the issue is that, I mean, the photo Z's that you get are calibrated on all galaxies, not the ones that host supernova. And if they are systematically different, the ones that host supernova, then your photo Z's would be off.
Yeah. So the systematics of photo Z is arguably the biggest challenge in the entire analysis.
Right.
I'm not holding back on that, and we have, in the paper we have listed the main smoking gun challenges, and the top three are exactly one of those is what you mentioned, and the photo Z systematics related. At the moment, we did a very simplistic approach because we wanted to fix the pipeline. At the moment. But there are people who are in talks of a follow-up with adding those complexities, but not yet. Yeah.
Thanks.
Yeah, maybe I missed this, but are you planning to blind the analysis?
I don't see who is talking.
Me. It's
Oh,
me.
oh,
Me.
sorry.
Yeah. Yeah. Are you planning to blind the analysis? Because there are many supernova analyses even now that are not blinded. And I think at this level of precision that we reach even now, and even more with the LSST, it would be very, very important to blind, actually.
Yeah,
so can you, is there like a explicit plan to do this?
Yeah, we've had discussions of this internally. The problem is that it's, again, we're using NARS Perlmutter, and then there's computationally there's a lot of resources being pulled out just by us. And given that the LSST is going to get already live, and we're figuring out, so the main challenge at the moment is how much of resources we will have to run again everything, but because we're talking about few months and a lot of
why is that related to blinding? I mean,
not even blinded. If I were to just run my analysis again, reanalysis, it's a lot of resources. So we're kind of stuck at the moment. So,
right,
but yes, I mean, if computational problem is not a problem because there's a roadblock there, we would like to do a blind analysis.
But I think you should really build it into the entire process. That would be very important.
By summer next year, we should be ready, and we don't know if we have already that much time on the hand. But there are many other things like the systematics that we would like to apply those and etc. Class check alternate classifiers and the classifier efficiency. Anyway.
Any final questions before? Very okay. So maybe Subha, you can set up your talk. It's already there.
So coming back to Arman, sorry, Arman, I didn't mean to.
Well, I wanted to comment on Alex's point. So
I wanted to just comment before that. So you mentioned about if you were to use only like pure. So this is that. So if I compare this with only a spectroscopic sample, now what the thing happens is like, okay, you have very good estimates of your sigma mu is very good over here. But as you go to a higher redshift, your statistics falls off. So your sigma blows up. And that's why the gain you get from photos, because even a higher statistics at the high redshift, so that affects on your dark energy estimation, right? You wanted to comment about that? Thank you.
Yeah,
okay.
so let's thank Ayan again for a stimulating talk. So next talk is by Subha, who will talk about a new distance indicator. I'm very curious what that is. He isn't told what it is. So. Yeah, so 35 minutes talk and 5 minutes discussion.
Oh, thank you.
Okay, 15 minutes.
Yeah, thank you. Oh, it's here. Come on. Hey, are you going to? Hello.
Yeah, please start.
Okay. First, let me thank all the people in the organizing committee for inviting me over here. I mean, RRI is very special to me. And Tarun is not here, but Tarun knows that it's very nostalgic for me. During my PhD in Indus of Science, which is like a kilometer from here, although I was a student of ISC, I spent almost all of my time in the room below this auditorium. There was a computer center. I hogged one of the computers. I was not a student of RRI. The newer students didn't know I was a student of RRI, so they didn't bother me. I just put my books over there. I just was always over there. And since this is nostalgic and I'm back over here, I realized I'm giving a talk in RRI after 20 years, actually. My first encounter of RRI was not very happy. So I have come to give interviews for Institute of Sciences, and you also came to give interview in RRI, and I didn't go to IIA and RRI because IISc did not pay you travel money to come to Bangalore. Only if you get selected, you got to. So you got to know that much later. Whereas RRI gave you money to come and also some money. And so I came here because I thought I would get the money over here. You give a written exam in the morning, in the afternoon your results are out, and if you're selected, then you go for interviews. So I went there, I saw, okay, I have been selected. So then I didn't want to come over here because I already had some offer somewhere else. So I went to the admin and said, okay, I have come over here, I've fulfilled all the requirements, why didn't you give me the money? And they said, nothing doing, you have to give the interviews, only then you will get money. And in those days, there has to be 2 interviews. So I was stuck for more than 2.5 hours in the interview, one committee and the next committee, and then I got the money. So I was very pissed. Anyway, so yeah, I got the job, but I mean, I had, but I got the job over there also, so I went to ISC. Yeah. So last week when Tarun was in TIFR, and Tarun told me to say something which is not mainstream. I was thinking of talking about machine learning in cluster cosmology and how the Planck tension of sigmoid between clusters and the primary CMB doesn't happen that much if you really machine learn the mass. But since Tarun is not here, so I'm going to talk about non-thermal secondary CMB, which is sort of a little futuristic, and then very speculative, something that will come at the end. This is a work which has been done basically by Sandeep Acharya, who is a postdoc now in IA, extremely smart person. He's in the job market for a faculty position. Okay, so this is where we are right now in a sense. Lyman sort of talked about the primary CMB, of course, went a little bit around here. And SPT Act, they, of course, a lot of science is about the secondary CMB, which Lyman didn't talk about yesterday. And these are mainly, till now, thermal or kinetic SZ effect from clusters of galaxies. So that's the age of the secondaries, which has been here for the last 20 years. I'm going to say that there is a second age of the secondaries, which is possible, and when, I guess, when people, sort of get bored of doing thermal SZ and kinetic SZ from galaxy clusters, they can do all these things. So we have this high redshift JWST galaxies. They can have bubbles around them. We can have SZ from there. You can have quasar bubbles before ionization. And today I'm going to talk about radio galaxies. Okay. And these are very interesting. And especially I'm going to talk about something which is not thermal SZ and not kinematic SZ, but non-thermal SZ, which is never done almost. So non-thermal SZ is just scattering of photons, okay? And so we can go beyond thermal. And the main idea is that it's scattering by a population of electrons, which has a power law. So this power law in this gamma, okay? So there is a power. And what you measure is, of course, the distortion fluctuation intensity, where now this frequency-dependent part is non-thermal, instead of what we generally see as the thermal SZ frequency dependence part. And the interesting thing over here is that just like the thermal SZ, this can be calculated, and this is also very, very unique, okay? So to basically see a little more, you have the electrons or the plasma, which has some pressure, and one can look at the upscattered photon spectrum and basically do this whole thing, look at the distortion and find what is the fluctuations in each bin. And if we do that, we get something over here. So people are used to seeing this black one, which is the YSZ distortion, the thermal SZ distortion, which has this dip and the upscattered part, okay? And there's the relativistic SZ if we correct for relativistic electrons. Then there is, the kinematic distortions, whether it's going away or coming from us. But then you see there's this green one, which is very different. And this is the non-thermal SZ distortion. And this depends on, of course, the spectrum of the electrons. So basically the alpha, and also how low in energy the electron energy density goes. Okay. And it is inverse Compton, yeah, but done in, yeah. And always. And you can see if the energy is, if the spectrum is too light, the energy is too much, then you can, really upscatter and just throw it out of the CMB band. So these lines are frequencies which will be available for the next generation, like the seventh. Well, yeah, it will just go out to some, not the CMB, it'll just go into hard X-ray. I mean, it will go to zero much later, yeah. Depending on, so I mean, I can have something which will go to zero over here also, yeah. And the idea is that if I have multiple frequencies as in the future, for example, for Seventh Observatory, one can disentangle these things. And one can actually basically get this out if and when everything else is there, with many sigma. Okay.
So overall it changes the slope?
Which one?
Overall it changes the...
Slope, the crossing, everything changes. I'll show you in a moment. Okay, so this is one interesting picture. So as I said, the scattering is by our power law of electrons, and depending on your power law index, so you can think, okay, this canonical power law index of 3, or people have been talking about something smaller or higher, 2.3. You can see the between, so let's take the black one and this one. You can see if this index is changed, your shape changes, you're basically going from the crossover changes, okay? So it's sensitive to the power law form of the electrons. Also, it is sensitive to what I call the minimum energy. So if I have the electrons going, and at what energy it stops influencing, and this is something which is unknown, actually. So models of radio galaxies, or people don't know. People have talked about P minimum of 10, 5, I think. Depends on what your P minimum is, whether it's completely relativistic, go up to 0 or not. Again, yes. And there is enough information, and with this kind of frequency dependence, you can actually get this 2 out from your measurement. Okay. So this is what Sandeep showed in a paper in great detail. Okay. And so we have a unique non-thermal SZ spectrum. The important part is unique. And the spectrum can explicitly tell us about the energy slope alpha and the energy cutoff of P minimum. These two things can be uniquely done. Okay. So now that there is a non-thermal SZ effect, we need to have a source. So people have talked about non-thermal SZ in clusters, and that's a bad idea because it's dominated by thermal SZ. You can only put some upper limit saying, okay, this is the amount of non-thermal SZ. Okay. So there has to be some other source, and this is where I went back 20 years during my PhD. So during my PhD, I was talking about radio galaxies. So I can see the history of CMB observations is 50 years old, secondary CMB. Studies of radio galaxies are 70 years old. And now we can combine these two, because secondary CMB and this radio galaxies have a lot of non-thermal electrons. So this was my PhD at 20 years old. Yeah.
What does that mean, 1 + 1?
That you'll come to in a moment. So you can get something out of this, you can get something out of this, but combine these two, you can get something more. So this was my last chapter of my PhD thesis, where you can see I talked about SZD from radio galaxies. And my thesis examiner, one of my thesis was Mark Barkinshaw, who has done SZ for many, many years. And he was very pessimistic about this. He said, like, I have tried long, you cannot measure it. So you cannot do it. So, but something changed. Something changed in the last 7 years, because whatever Mark thought was never going to be possible, that happened. So this also has an RRI connection, because Malu was a postdoc over here, and Ravi Subramaniam was over here, and they detected the first non-thermal SZ. Yeah, from radio galaxy. So they used ATCA. Okay, so here is a large field. Here is the cluster. Is actually the bullet cluster is the X-ray map. This is the radio map, and then you go over here. This is the radio galaxy, and you zoom in. This is the non-thermal SZ, and you zoom in. Here is the non-thermal SZ. So here is the galaxy, the center of the galaxy, and here is the lobe. And this is the hotspot over here. And you can see it's non-thermal SZ. Non-thermal SZ is actually all over. This is from 18 gigahertz, the green one, which has a higher resolution beam. And this is from 5.5 gigahertz. So they first detected non-thermal SZ from a source, which is a radio galaxy lobe. Okay, it's a 6.5 sigma detection, and it had minus 88 microjansky per arc minute squared kind of distortion, which for them, because only they didn't have many frequencies, so they had to just assume one frequency, which was like delta T of 1.5 microkelvin. Y, where they didn't really use the exact non-thermal spectrum, they just used a simple thermal spectrum. Their Y was around 2.
This is moreover known. Why are you calling it S and Z did not discuss this? It's like you said, inverse Compton.
SNZ, in the first paper, I don't think it discussed it, but there are papers after that which has discussed this thing.
Yeah, but it already has a name. It's
Non-thermal SZ.
scattering.
Well, so that's I call non-thermal inverse quantum catenary Sunyaev-Zeldovich effect. Yeah,
Fine.
yeah, yeah. Okay, so this is there. So now we have non-thermal SZ in theory, and we have non-thermal SZ also detected. Okay, and here it is. So we can think of something to do with it. There's one source over here, which basically means there are many, many sources. There are no dearth of radio galaxies and radio galaxy cocoons in the universe. Okay. Now, realize that this one, other than the SZ distortion, also, of course, has the observed radioluminosity. So we have two things. Previously, there was only observed radioluminosity. For every radio galaxy cocoon, there was radioluminosity. That's the data. And with one data, or just you are very restricted with how you can model the radio galaxies. But now you have non-thermal SZ, and you have like 2 points. Remember, and remember that you also have alpha and a P minimum from C again to CAB. So we can think of radioluminosity and non-thermal from this radio lobe. So the history of modeling radio galaxy lobes is a long history. I mean, and people have done simulations. I don't want to go. This is a very nice, very recent review. But the idea is that although it's messy, you can model it. Okay, it's very much like galaxy clusters. Galaxy clusters are messy, but we can model it. And a simple answer to a question which always I get, I want to have given it, is like how much difference is between simple modeling and simulations, is that, I mean, the idea is that it largely validates this Kaiser-Alexander picture of radio lobe, how it expands, what happens. The only thing is that we cannot get the turbulent part of it, right, because it's simple model. Okay. So to give a picture of the model, I'm not going into detail. I'm not an expert. So this is sort of radio galaxy, center, the two hotspots, and there's a cocoon, a lobe. And what you need to do is that you have to model it so that you can do its evolution in size, pressure, luminosity, and match with the observations. And now we have two observations. That's the important part. With one observation, it was very difficult, just radioluminosity. And now we have two observations. So this would be a cartoon of a radio galaxy model. You have a central engine. You will have the hotspots. There are two length scales. Both of these expand. They're more or less self-similar. You can, of course, do it separately. Typically, observations show that this axial ratio is roughly 2 for all the radio galaxies. Okay? And in between, there is this non-thermal plasma. It's like, you have a water pipe. You have a hose. It goes and hits the wall and sort of flows back. And this region is the non-thermal region, which is full of non-thermal electrons. And this is what the Malu observation looked at. This is what they found. They found this part of it. Okay? So if I look at this scale, this length scale is like Lj, some length size. So this is twice Lj. And this is Lg, because this is an axial ratio of 1:2. Okay. Given that we have a model, I'm not going to describe the model at all. What we can show that the way, if I start with some population of electrons, somewhere at some redshift in a coil, depending on what was the spectral index, the high energy ones will lose energy and sort of drop out. The low energy ones will continue to pump energy and push it. And so the low energy ones, having the low Lorentz factor, are important. And it sort of mainly controls the evolution of the lobe. Okay? If I take that population, and of course, in this modeling, I have energy being taken out in synchrotron, energy being taken out in inverse Compton, and energy being loosened because it's working. So there's energy that's hitting up the ambient medium. You take all this thing, you can model what will be the radio power, given what is the intrinsic jet luminosity, and of course, how long it is. So when the jet is on, depending on the intrinsic jet luminosity, you have some radio power, which goes, and when the jet sort of dies, the radio power falls. Okay? See that this radio power, depending on what is the intrinsic luminosity, depends on the size of the cocoon. So with time, the size of the cocoon is larger, the radio power falls a bit, because energy has been lost. And then, of course, once the jet is no more, the cocoon doesn't expand very much, and the radio power falls very fast. Yeah.
That will also have a frequency dependence, the radio power.
Radio power is at some frequency. Yeah, it has a frequency dependence. Yeah. You said,
I just said 15 minutes.
Yeah, that's fine. I'm doing well.
The radio is primary synchronous.
Radio symmetrical emission. So this was all that was there before. We could model this. Now we have something extra. We have now an observation which gives this also. And over here, as you can see, the Y non-thermal also depends on your Q and depends on the size of the cocoon. This is the real size of the cocoon. So at one size of the cocoon, for the same Q, I have one value of Y and T, one value of radio velocity. So whereas previously the models would not be able to constrain the model, now because of this two-dual observation, we have tracks in the LR-YLT plane. Okay? So depending on whatever is your lifetime of the radio jet, whatever be your Q, you have these tracks, okay? And depending on where you have your measured Y and your measured radio power, that gives a track. That gives a point in the track. And especially these subtracks sort of merge over a certain radio power. So this is kind of observed radio power. Okay. Which tells you that now, because we had this two information, previously didn't have this, we have this model which describes the evolution of the radio galaxy and its internal energy completely mapped out. Okay. If I get a point over here, I know what is the model. And also remember, the CMB gave me my alpha P and the P minimum. So previously I could only get LR, now I can get LR, YT, alpha P, P minimum. Everything is fixed. Once I know the two observations, there is no more, the model is fixed. Okay. So this additional information from this non.
But you can also get the size of the cocoon just from the radio observation.
Yes, I will come to that. Yes, that's what you see. The size is what you see. So that gives you the size of the cocoon. Yeah. So the additional information gives you a fixed radio model. So the first thing we can do is that we use this to the Malu observation. And this was the first time we could say that the limit on the P minimum, where it goes, to give the Malu observation is like 1 to 2. It almost goes to the non-relativistic. Okay. Now I'm going to use this. This is the more futuristic thing. I'll come to the speculative part. But before we proceed further, we should also look at this. Our universe, of course, is full of radio galaxies. There are many radio lobes. You have models of how many halos would have radio lobes. Okay? And so this will also give you a resultant secondary CMB fluctuation. There will be a mean YCL, and there is no escape from this. And it's going to be there. Okay? And again, Sandeep wrote a second paper on this in detail. But I have only one slide. This is the most interesting part of it. So over here is the distortion as a function of frequency. And of course, I put in everything that typically will look in any CMB observations. What I want to show over here is that this line, this one, this is the mu distortion, one of the holy grails of future physics, right? This is what we want to do. Tells us about the early universe. And this one is what will come from the non-thermal secondary anisotropies from all these radio lobes lying around. So if I want to do mu distortions, you cannot ignore this. You have to have this. So there's something you should, again, worry about. You cannot say you're going to go down and one day find mu distortions. You have to be, it's there. Okay.
How do you get a mu distortion at such late times?
No, this is mu distortion not for late times. This is just a mu distortion for early times. It's just to show that the mu distortion, how. Yeah. Which one? This is a square, and so it's pressure turnover from. Yeah. Okay, so now let me go to the more speculative part of it, which is what I promised Tarun. So this was not speculative, this is futuristic, and I think we should look at it. This is what, hopefully someday when people will do more than clusters, they will look at it. So this is more the rethinking cosmology. So here's the Hubble from bubble. 10 minutes, perfect, yeah. And this is speculative because this is, from Lewis Carroll. Well, sometimes I believed as many as 6 impossible things before breakfast. This is after breakfast, before lunch, but still it's true. So this is a collection of Hubble constants, okay? There are many plots like this. It's just one of the plots. You have this indirect measurements, which is like CMB, BEBO, and then there's a direct measurements over here, and talk of tensions and stuff. Over here is one with distance ladder, and over here is one without distance ladder. Okay, and X-ray clusters is one of the first things that people did to do Hubble constants without the distance ladder. So let me talk about just one slide about Hubble constant clusters, because students over here. So when we want to do Hubble without distance ladder using galaxy clusters, and this is from 1978, okay, we need both X-ray and SZ observations, thermal SZ, and of course we also need the temperature of the cluster. And the idea is that your delta T by T goes like NKT, and your X-ray luminosity goes as n squared T half approximately, and you can get rid of the n, the unknown density, by taking ratios of this, and you have an estimate of the physical size, which depends only on the SZ observation, SZ flux, SZ flux, and of course you need to know temperature. And this DL basically gives you this estimated physical size by the size that you see on the sky, which is the galaxy cluster that gives you dA. And people have tried this. It has a very checkered history, lots of scatter. You can look at the dA. This is all before 2006 and 7. And then there was a big gap, and then this is like post-Planck. And this is the Hubble diagram with Hubble clusters, galaxy clusters. Okay. So remember, this is what was the way of doing a distance-independent, the distance ladder-independent Hubble constant measurement. And you can see, initially there were very few clusters, and then later we have like more clusters, and with Planck, after Planck, there are like 67 clusters, and now we can get a pretty good measurement, actually. So people should keep this in mind. People always seem to think that Hubble constant from clusters is very, very bad. It is not that bad now. I mean, if you do it carefully after Planck, it is not that bad. So you should keep this in mind, even with some systematics. Okay. So this was for 40 years, okay, from 79 to 2019. Let's fast forward to 2025. And let's try to get the Hubble from this radio bubble. Okay. So I will give a back of the envelope thing. I can do it. So remember, this alpha P and P minimum, this is given from the spectral shape that uniquely gives you these two quantities. The radio synchrotron power I can calculate, okay? And you can show the radio synchrotron power is basically N0 squared. It's LJ. So LJ is the, I told you, is the size of this lobe, right? Cubed. I can calculate the non-thermal SZ distortion again, fully. So this is when you do it correct, and this is when you just do it hand waving, okay? And you can see this is N0 times LJ, okay? And so just like in galaxy clusters, I can have an estimate of LJ from a measurement of the radial luminosity and the non-thermal SZ, okay? This is just like in galaxy clusters, right? Of course, there is all this alpha P, and these things I'm going to know very precisely from CMB observations, okay? And so this is how precisely, for example, something like Simon Observatory can give you. Slightly simply done, but you can get this very, very quickly. At present, of course, there's only one measurement, and so we have to take what this measurement gives us. This measurement actually estimates alpha P to be 3.2 because it has a spectral index of the radio power, and the radio power spectral index gives you the power of the electrons by this, so they get the 3.2. If it was 3, then the energy would have been equally distributed between the kinetic energy, the energy of the cosmic rays and the magnetic field, but it's slightly different. And this is what actually simulations tell you, okay? And so you can get this very well. And because you can get this very well, you can estimate this very well. Okay. So this is how you can get an estimate of the size of another kind of tracers, which is like galaxy clusters. But we have one of our objects already there, so you want to apply it to that and see whether it makes any sense. Okay. So I go back to the track that I told you. The size of from the center, the galaxy to the first lobe, is 4 arc minutes. Okay. And this is their YNT, if I correctly take into the spectral function and their radio power. And this will be sort of the track. So that's like an estimate of 1 megaparsec for this Malu radio galaxy. And this radio galaxy is around a redshift of 0.3. This is actually a bit uncertain. We think it's a redshift of 0.3. Okay, so this comes from the radio spectral index, average spectral index, and this is something that we found out that it goes up to P. So the estimated physical size approximately is 1,000 plus minus around 300 kpc. This uncertainty basically comes from the band in LR, mainly. We have not taken any uncertainty because I've fixed this too. This should also give you some uncertainty. Given this, given the redshift, given the size, this 4 arc minute that we size, what do we get for distance? Here's the distance for this one radio galaxy that we have observed. This was the scatter distance from the clusters. And here is a list which I showed before. Now remember, a few years back, there was this one detection of Hubble constant from this gravitational wave siren, where it had this electromagnetic counterpart. And the number of 80 was 70 plus 12 minus 8. And people have done many, many other more involved calculations with more systematics, 70 plus 35. So this is the gravitational wave, this one. And what do we get for our radio galaxy? This one. Not bad. It can be a fluke, but it's not bad. Now, these gravitational waves, which we all looked at, is fantastic. It will become competitive around 50 detections approximately. That's the kind of aim. But we have to get the electromagnetic counterparts. Right. Radio galaxy lobes are easier to find. It's lying all over. One has to just go and do it. I mean, someone has to get convinced that this can work, try it out, and do it. In fact, I compiled a list. I mean, this is like many sigmas with something like a Simon's Observatory or something. You can. And so not only an 80, I can get an H of Z, because these are at different redshift. I don't know whether this all be observed by SO or not, but I mean, it's impossible. And one can do a greater list. This was a very quick list that I did. You have a question?
The 10⁻⁴ signal that you got for the Malu radio galaxy Y is very large, but look how you look at it.
0.3 redshift, yeah.
So is there any indication of the magnitude you would expect from these other galaxies?
So radio galaxies are quite, I mean, the problem was that it was non-thermal, and so 10 to minus 5 sometimes. It depends on, so these are all these magnitudes that is expected. You can see most of them are quite large. These galaxies which will give large are basically compiled over here. So I mean, 10 to minus 5 is typical. It depends on how big, how much the globe has increased. If it's increased very much, then the power dilutes, the Y dilutes. Okay. If it's within a cluster, then it's actually even overpressured, and that's even more. But I think we'll have to subtract the cluster, which will become more difficult. So it's a potential gold mine if one believes in this new way. And this is a new way of doing Hubble constant with distance-independent ladder after 45 years. So one should be, I think it's good for a conference. This sigmas as how well we can get it, detect it. I know, this is very, very, it's just take in the, don't take this very carefully. So look at the signal to noise, and this just is, yeah. So it's not, but it basically says that we can get it at much higher signal noise of the radio detection, yeah. So let's rethink cosmology over lunch. That's, yes. Right. Right. Okay. So radio galaxy is an elongated thing, as you know, and typically I would love to have a radio galaxy where I can see both the hotspots. Okay. I don't want, so there are many which you can see, just like the picture that I showed. Both the hotspots. You don't want it too elongated like this. The criteria, so, and you know that typical observations tell you that the axial ratio is 2:1. If the radio galaxy is slightly old, it becomes 2:1. So I mean, have done it two separate evolution, and as the time goes, it sort of becomes 2:1 and then evolves the same ratio. So that's like a ellipsoid. To see the two hotspots, there is a criteria that it should not be less than 35 degrees on the, with respect to the line of sight. So it should, okay. Given that, your answer is very insensitive to your, so what happens is that, remember, the size is fixed on the sky because that's what you're looking at. So you have to have a radio galaxy. Either it is long but with large, close to 35-degree inclination to the thing, or it is small but with, now the Y is along the line of sight, right? When it's large, your pressure has dropped. Your pressure dropped into, but line of sight has increased approximately. That number is more or less same. So that doesn't change. The total radio flux is what you're measuring. That doesn't change. Your result is very insensitive. No, I mean, so it's tilted. Yeah, so you can, depending on, as I said, if it's not, let's say if it's 40 degrees, it was like 60 degrees, you still have to have the same size. So that tells me how large it can be. It cannot be very large because then the size, because, so this size, pressure, and the distance that you go, these are like inverse, and that cancels. And so there is a small change, but not that much.
Yeah, see? Okay.
I must say, I didn't know you were working on this, and I'm extremely excited by it because I think that SO is going to turn to this in a big way, but from a completely different direction I'm coming from. So my former graduate student, who's a postdoc at in Spain, Martine Locan, she's worked with me on things that we've championed, which is oriented stacking, where you use large-scale structure. And the most recent work we've been doing on that is with, we need SIMS, and we got SIMS, the Flamingo and other simulations. And what they are putting in now is oriented jets for how their energy is going in because, you know, the feedback for the holes. Yeah. And so what we found with these theoretical things, which we're going to relate, in fact, to ACT data, is this oriented issue of seeing both the jet and then the far field. And of course, it's a non-trivial thing because they interfere with each other in the beam size of SO and ACT. I hope you're listening. I am. Is that it will fuzz out things. And so we've been using this looking for superclustering. And so it will become an interference issue, yes, which will mean that you'll have to try and get very good information as a function of depth out. But the key thing to go after this with the CMB is to do what I think will be the oriented stacking, but in away, which we do in terms of what is it as a function of scale. And that's pretty interesting because you can do a multipole expansion and you get information on each multipole up to 4 actually. And that is much cleaner than sphericalized measures. And so I think there's a real huge future for this. So I'm glad you're onto it because we can chat about it.
Sure.
I think Asim.
Yeah, no, very interesting. 2 quick questions,
Yes.
mostly because I don't know much of the physics here.
I don't know either. So
So first one, does beaming have any influence on inference of sizes, etc.? And secondly, are the redshifts always straightforward, quote unquote, to
yeah,
measure?
so for the redshifts, you need to know the central galaxy. That was the biggest problem over here. So the Malu paper does not give a redshift. So what we had to do was to cross-correlate with, and saw that there is a galaxy which is very almost on top of the central source to get the redshift. So that's, yeah.
Maybe we can chat a bit later. Some months ago, we were thinking about projects involving trying to learn redshifts from radio data itself.
Yeah. So, but the beaming is not.
So just one comment. I mean, in '98, I think there were one claim of acceleration was from type 1a supernova. There was another claim of acceleration from FR2 radio galaxies by Ruth Daly, who at that time was a faculty at Princeton. But that, as I understand, fell through the cracks, okay, because of systematic. So, so can you do like revive that technique also beyond just the Hubble constant?
I mean, it all depends on how good you think is the modeling. I mean, I think what needs to be done is that some simulation guy needs to be excited about it and calculate the y and z in a simulation. People don't do that, first of all. And also, I mean, in the simulations, this energy loss as a function of time is not always very nicely done. Okay, and also a little bit of important thing which we don't have actually over here is that how much of the electrons diffusively leak out of the thing. Over here, it's all, the electrons does not leak out, it's all over there. But these things, I think, will change the alpha. So when you go to CMB spectrum, this will effectively change your alpha P, what you get, and because this leaking out will change your alpha P, right? It also change your P minimum because the energy. So the CMB spectrum will nail this thing. We don't have to go into the more details, but it's just nailed by this tool.
Yeah, Arman?
Shubha, can you show the potential sources that you were?
Oh, that's the weakest flaw. Do you want to go?
No. So some of these guys are at very different redshifts, right? So I can see one at 1.7. So the properties are similar. You can model them in the same way, or you can assume a kind of a redshift evolution.
Yeah, to be honest, I don't know. I mean, this was a more or less.
My question is that would you consider the redshift or time evolution for the sources, right? I mean, because as long as the precision is small, it's interesting. But if you get a higher precision, that very little percent accuracy matters, right?
Yeah, I agree.
So then there would be some way that one can calibrate them, considering their age
Yeah,
evolution.
I think these are questions which are much ahead of what can be done. This is like the first idea that's been there. Now one has to look into it. One has to look into many things.
It's certainly interesting,
especially.
But these are confirmed redshifts of these radio galaxies.
Yeah, these are confirmed redshifts of radio galaxies. This is just from a radio galaxy catalog. You know.
I think Raman is worried about the modeling of the radio power.
Yeah, radio power stuff. Yes.
Okay, any other questions? Yeah, Subodh.
It's actually a very naive question. So these radio lobes are huge, right? And so if
we are looking at huge radio lobes.
Yeah. So if you spot one, how do you know definitively it's the galaxy that you think it's with, rather than something maybe close by in the field of view?
No,
right?
I mean these are. I mean the central radio, the source shines so brightly in the radio. It's almost, you can see that it's just black out. It's so extreme. And you can see, if you look at a galaxy catalog, you will see a galaxy which is very in that. Of course, there you have to take some circular annulus and see whether this galaxy is exactly over there. And this galaxy, you always find a galaxy which is really close to it. And that's sort of the central galaxy which is giving the jet. So that small uncertainty will be there. But that small uncertainty does not change the LG uncertainty. LG is so much, the galaxy is very small. What is more important is what is the density structure. So depending on, so you have to be careful because when the jet goes out, the energy, the way it loses, the whole energetics also depends on in which density structure it moves, surrounding density structure. So
how good can you be then of this integrated constraint that you get that you say will be sort of like a working with that?
This will be?
From the
yes, as a?
You show that it actually is above the
yeah.
expected mean value.
Yeah.
So how confident are you?
I think that's yeah. So that's I think is where I'm quite confident of that. It will be. I mean, you can always play around a bit over here because there are. So what goes in the modeling is how many radio galaxies do you expect in a volume, right? And so there are people have done. So you can do some modeling, or you can also go to observations where they map the density of radio galaxies with the density of galaxies, and you can do that. And so you know what's how the radio galaxy density goes as a function. And so for each of these radio galaxies, you know the LR, and basically you can connect it to the luminosity is connected to the black hole mass in some sense with some efficiency. We don't have to, these are not done with very high efficiency, so this is like quite low efficiency, and you will get it. I mean, it can be bigger also.
Sushmita?
Yeah, just a quick clarification. So, about the traveling radio, so these are typically, they extend outside of the radio as well, right?
Yeah, these are all, they go out of the galaxy and they just go out.
Right.
This
And how far they can go depends on the gas density that it
yes, typically these are, many 100 kiloparsecs, megaparsec size. These are giant radio lobes. Yeah.
So you need to know the gas density out to a large.
Approximately, yeah.
Okay, any other questions? Okay, so before we leave, right, since everyone is telling personal stories, and I also want to relate an anecdote from history of cosmology, which you won't find in any textbook, okay, or any paper, okay, and this is mainly directed at the students, okay. So in 1979, it was Einstein's birth anniversary symposium, and there was a conference at Cornell University, and there Lyman's former colleague, Professor Robert Dickey, gave a talk on discussing what we now know as flatness problem, horizon problem, and so on and so forth. And the write-up of the talk is also published in Hawking and Israel Einstein Centenary Survey. So when he gave that talk, all the astrophysicists in the audience ignored what Bob Dickey had to say. And the list of people in that room were, I think, who's who of astrophysics: Tommy Gold, Ed Salpeter, Hans Bethe, Saul Tucholsky, Stu Shapiro, and many others. Only one unknown person who was about to quit science took what Bob Dickey had to say seriously, and the name of that unknown person was Alan Guth, and the idea he came up with is inflation, and the rest you know is history. So this is a story I've heard from Ira Wasserman, who was at that time was a newly appointed faculty at Cornell University, in fact is still at Cornell University. So anyway, the lesson to the students is important to think differently from the bandwagon or differently from what you're taught from advisors, okay? So with that, I think we can go for lunch, I think. So we'll meet at 2 only, right? I think we already, okay, so we'll reconvene at 2:30.
Is that right?